This is a material with a very long name. It's yttrium barium copper oxide. And it doesn't look like very much. There's very strong magnets here, and it's not responding to them. It doesn't conduct electricity. Doesn't seem very interesting. But when you cool it down, it changes completely.
Using liquid nitrogen, we're reducing the temperature of the disk to minus 196 degrees Celsius. And now, when I bring it close to the magnets, something unexpected happens.
It's levitating. And it will scoot around on the little track here for quite a while. So something's changed. You cooled it down, the behaviour changed completely.
And that's because cold has altered the material at the atomic scale. Materials conduct electricity when electrons travel through them. But the atoms in a conductor are an obstacle to the flow of electrons, because as electrons bump into them, they lose energy. At extremely low temperatures, the electrons can team up into pairs. And then, the attraction between the electron pairs helps them navigate through the atoms far more easily. So when I bring the disk close to the magnetic track, a strong electric current begins to flow in the disk. This in turn generates its own magnetic field. The magnets in the track and the disk repel each other, and so the disk levitates.
This is an example of superconductivity. Once it's cooled down below the critical temperature, the properties of the material change. It becomes able to conduct electrical currents without any resistance. And that also changes how it responds to magnets.
The peculiar electromagnetic properties of supercooled materials have given us a powerful new tool in engineering and medicine. Some countries already use a supersized version of this magnetic levitation effect in their high-speed rail systems. Having no contact with the track, trains run faster and more smoothly and efficiently. And inside MRI scanners, liquid helium supercools massive coils of copper wire to a temperature of minus 269 degrees Celsius. At this extreme cold, an electric current can flow with almost zero resistance, which helps generate the powerful and stable magnetic field that the MRI machine needs. The extraordinary discoveries we've made at extremely low temperatures are now driving one of the biggest scientific quests of the modern age. How cold is it possible to go? And how do we get there?
We know that as you cool materials down, they tend to turn into liquids and then solids. But actually, the question of how cold you could make something started with gases. And this was the kind of experiment that was used. What I've got here are 4 beakers, each of which is at a different temperature.
They range from minus 5 to 50 degrees Celsius. Into each, we're placing a syringe containing 15 millilitres of air at room temperature. This air will heat up or cool down until it's at the same temperature as what's in the beaker.
So much science is about waiting, and this is one of those experiments.
But it's not the change in temperature that's interesting here, it's something else. After 5 minutes, the air that's heated to 50 degrees has expanded from 15 to 16 millilitres, while the air that's cooled to minus 5 has reduced to 14 millilitres. In other words, there's a direct relationship between the temperature of a gas and its volume.
So the first scientists who saw this kind of relationship did something very straightforward. They plotted a graph that showed temperature against volume. And at the higher temperatures, the volume was higher, and as you go down to the lower and lower and lower temperatures, the volume decreases. And then there's a question, because at some point, even though they couldn't see it, if that line kept going, it was going to pass through zero volume, and at that point and past that point, what happens to the temperature? What does it mean? And that was the first hint that there might be a limit on just how cold you can go.
This observation led to a concept known as absolute zero, the theoretical limit of cold.
And now we know exactly what it is. On the Celsius scale, it's minus 273.15, a fantastically low temperature, but below that, there's nowhere to go. That's the coldest you can get.
And it remains a theoretical point on the temperature scale. The Boomerang Nebula, 5,000 light-years away from Earth, is the coldest place we know of in nature. It's a star in the late stages of its life that's shedding huge plumes of gas. As this gas expands rapidly into the void of interstellar space, it loses energy quickly, resulting in its unusually low temperature of minus 272 degrees Celsius. But even this is 1 whole degree warmer than absolute zero. Though we've yet to find absolute zero in the far reaches of the universe, we're trying to create it ourselves, much closer to home. At Imperial College London, Professor Ed Hines and his team are working at the very limits of the ultra-cold, within fractions of a degree of absolute zero. It promises to open up a whole new world of physics, which could revolutionise our future. The stuff they're cooling here is tiny clouds of molecules. Chilling them to absolute zero requires 2 phases of cooling. First, using liquid helium, they take them down to within 4 degrees of absolute zero. But it's these last few degrees that pose the problem.
There are ways to make helium a bit colder, but to get to the millionths of a degree, there is no fluid that you can use. So instead, we use light. By scattering the light, the molecules will get colder.
Even at this temperature, the molecules still have some movement. Photons in the laser light collide with the slowly moving molecules, and in that instant, what little momentum they have is transferred to the photons. The photons are scattered. But the molecules slow down, and so get even colder. By using an array of different colours of laser light in just the right order, Ed and his team can reach temperatures within a few millionths of a degree of absolute zero. At these incredibly low temperatures, materials begin to behave differently at the subatomic or quantum level. In this quantum state, they exhibit strange properties, which might lead to a new type of computer. A normal computer bit can only represent a 0 or a 1, but these quantum materials can be 0 and 1 at the same time. Link these multitasking bits together and they can do vast numbers of calculations simultaneously, far faster than any conventional computer chip.
This opens up the possibility of quantum computing, quantum sensing, quantum cryptography. These are all ways of doing useful things, but much better.